Alright everyone, let's get back into it. So, I don't know if you remember where we left off last time. We were implementing the binomial heap merge algorithm. And so let's finish that up if we can, as quick as possible. So basically, what are the possibilities that can happen in a binomial heap merge? Let's talk about that for just a second. Right, so either, say one of the objects, one of the SuperRoots, remember I'm using SuperRoots to keep track of all my BIs, either they both have a B at index, or just A does, or just B does, right? And so here's the thing: if this one has it but we don't carry, then something happens. I think I missed a condition, else if. There we go. So there's another condition. So there's a lot of conditions here. So let's take care of maybe the easiest ones first. So remember that what we have to do is, if the superroot at B has something, then basically we just have to, we're merging these two things, so we'll copy it like that. Okay. And then maybe just for safety, just in case it'll delete everything, we'll set this to, there we go. Okay, what's next? What's the next easiest thing to do? Well, what if we have to add something from superroot A, index, and p carry? So p carry means that at the previous index we had to add stuff together, and we're currently carrying into this index. So what that means is that what we're going to do is we're going to add these two together, and then we're going to have to reset p carry. So basically at this point, this is our first time that we actually have to check whether or not. So if the value here is bigger than the p carry value, then what are we going to do? Right? So then the point is that this one here is going to become the parent, the child of the index is going to become the parent. So is equal to p carry. And then I guess what we have to do here is we have to set p carry equal to this, and set this equal to null point. And then it's the same kind of thing the other direction. So here what we'll do is we'll say p carry, have to add one of its children at index is equal to superroot A at index. And as it turns out, then we don't have to update p carry, we basically just have to set superroot A to null pointer, and we should be good. Why does it not like this? It may not have been initialized. Good point. Okay. Whoa, what just happened? Oh, okay. So here we have to create a temporary carry, which is equal to something. And then what we're going to do is we're going to set I guess actually what we have to do here is we have to look at which one's bigger. So if the superroot A child index dot value is bigger than or equal to superroot B child index value, then we will merge B into A. So really, I think I should be using pushback for all of them, and then we will push back this one here. Why is it not like this? Ah. And then what we have to do is, if we already have a carry, then the thing here is going to be equal to the carry, and the temp carry, well, should be this one here. And then we'll set p carry equal to temp p. There you go. And of course, it's saying it's all unreachable. The reason is that we never actually have an opportunity to set it first. So we have to actually do, for instance, like this case here, where let's see, so here what we're going to do is we have to test if this one is bigger, then we merge in the p carry. So let's see here. I think basically what we do is we just do the same line of code except it's a B. I guess the only, so this is the condition that'll, okay, so this is our condition that gets us a P carry here. So if the P carry exists, else, what we're going to do is we're going to set P carry equal to, well, let's see here. So here we're merging into A. So I think all we have to do is set this, and then we set this equal to null pointer, and forget. So that should fix it. So this is the instance where that works, and then we have to do the else condition, which is basically the identical amount of code, except everything is done for B, and we push in A, and then here we say this, oh wait, B, B, and then here I think what we do we have to change this to B? If both of them exist, and we merged into B, then we do this, we do this, something like that. So the point is that there's a lot of code in this merge, and I'm not 100% sure if so there's an else condition here. Let's do the else condition. Here we need to do p carry children push back, and then we'll push back this one like that, and then we can set this to null pointer. Okay. So we're going to be children push back. So then we set Okay. Fair enough. So I think, are we finished here? To be honest, I don't have any idea. Oh yeah, we're not done. Because if there's more stuff... So this is only where they both exist. So there's more code that we have to do. Basically the point is that this is just... Maybe this is too complicated, but this is just the way that... Yeah. So basically I'm just dividing it into cases. I'm dividing it into the cases where we have BIs in both of them, or there's a case where we just have a BI here and we have a carry, or we have a BI in B and we have a carry, or we have a BI in B and no carry, and so in that case we have to transfer it over to A, because everything's getting merged into A. And then, yeah, so I guess... So we should also maybe have a max size, which I think I had last time. I just kind of got rid of it. And so what we'll do here is we'll just say, for int index equals, what is it, size plus 1, index is less than max size plus 1, index plus plus. And then basically, unfortunately, what we're going to have to do is we're going to have to even do more code. So, but in this case, there can only ever be... So basically the thing is that if only one of them is going to have a proper length, so I guess if like superroot a.children.size is bigger than min size, then we'll do 1, else we'll do the other, something like this. And then what we'll do, so if a p carry comes out, then basically if p carry and superroot a at index, children index at index, then what we'll have to do is merge them together. So if the value of this one is bigger than or equal to the p carry value, then we're going to have to do even more stuff. I'm sure there's a shorter way to do this. There's got to be a shorter way to do this. Then what we do is we merge this one, children, push back, carry, then carry equals this, and this equals null pointer. So there we go. Else, what do we do? Else I guess we do nothing, right? Oh no, okay, so else if p carry, what we do is we just stick it in that position. We say superroot a children index equals p carry equals null pointer, and so that's what we do there. And then we basically do the same thing for the B side, except I think we have to push back things into the A side. So we have to basically, instead of doing all this stuff, we have to so if the superroot B is bigger, then we push it back there, and so then we set that. here we'll have to add a null pointer to A because there isn't something in that position yet. I guess, you know what, the one way to do this, to simplify this, is to delete all this code and then just add null pointers into A. So basically what we do is we say if children hash tables will require no recursion. Something like this, then we can actually just append a bunch of for maybe this thing, and then I++, something like this, and just do pushback null pointer. So that'll help. And then maybe else if the other way, we'll just push back into B with pushbacks and null pointers. Something like this. So this is horrible. I almost wonder if this thing will run. I don't know. So, anyway, but this is basically the main idea. I don't think I'm actually going to try to debug this thing in real time. I think it'd be pretty horrible. I think the right answer is to go onto hash tables. But I think this is basically the idea, right? Basically, this is just binary addition, right? If this is 1 plus 1, then you have to decide which of the ones gets merged into each other. And this is 1 plus 1 plus 1. This is just 1 plus 1. This is 1 plus 1 plus 1. This is another 1 plus 1. This is 1 plus 1. Here's another 1 plus 1, right? Here's a 0 plus 1, but the problem is that we need everything in superroot A because we're returning superroot A. Superroot B basically dies off, or we don't expect it to survive. And then here is just what happens if you get a carry with nothing to add. So it's like 1 plus 0 plus 0. So that's what this is. This is 1 plus 0 plus 0. And that is not how you make a comment. Right? So, I mean, there's almost certainly a better way to code this up, but let me promise you that you're almost certainly never going to have to actually do this in real life. Okay, so let's talk about hash tables. I mean, it'd be nice to run this thing. I think I might have a binomial project that I've already coded. Maybe I'll release that on GitHub because I know that one works. Okay. Oh, great. Okay. All right, try again. So, yeah, we'll go into the project now, I think. I think that's basically the safest bet. So the project is implementation of a hash table. So let's just read through it while Inkscape loads. So here's Inkscape. It's loaded. Basically, introduction, we're planning a mass vaccination site. Okay. I mean, I guess who cares about the premise? We're going to use 2 different collision handling policies. So I'll explain what all that means in just a second. So a hash table is a data structure which implements the map ADT. Okay. It stores the pairs of key value. Okay, so that needs explanation. Let's talk about that. Okay? So basically, when they talk about the map ADT, which stands for abstract data type. What they really mean is something where basically what I want is something like an array, not quite an array. Like with an array, right, you store things by index, but here we want to store things by key. So here we want to store things by key, and then find them by value. And let me explain what keys and values are. So keys are, well, I think the simplest way to explain what a key is to think about it like this. And map ADT, for instance, is a data structure where you could have, like a phone book is a map. And so the question is, why? And the answer, well, okay, I guess actually an inverse phone book. An inverse phone book is a map. And the question is why? And I'll explain what I mean by an inverse phone book. So in an inverse phone book, you'll have a phone number like 123-443-2211, right? And this phone number matches up with a person, right? So, and that person might have some data attached to them, right, or whatever, but at least they have a name. So Jimson, right? And so that's, right, that's the person who is attached to that phone number. And then here's another phone number, 555-444-3333. And then the person here is Abby, I don't know, Bryanson, right? No idea, just making up. I mean, everyone is the son of someone else. So, and then you have another phone number, like 667, 889-0011, right? And who's there, right? So, Cicero. So, the point is that when you have a bunch of phone numbers, right? These are basically the keys, and the names are the values. And why are the names the values and not the keys? So here's the reason why the names should be the values and not the keys in this case, is because, for instance, there can be two people named Abby Bryanson, right? And they could, there could be two of them in the phone book, right? But they have different addresses, right? So the requirement on a key, keys are required to be unique, okay? If a key is not unique, then the problem is that we're storing things in the same data structure. So if you're going to use names as keys, then you should probably have some kind of other identifier that makes that name unique. Like, for instance, Abby Bryanson -1, Abby Bryanson -2. But of course, then the question is which one is which, and that leads to complication. But the point is that this like phone book type thing that I'm describing is an abstract data type. It is a map. What's another kind of thing? If you had, for instance, social security numbers that map to people, right? That's a map. What other kinds of things are maps? I guess maybe you don't know this reference, but like hull numbers to ships, right? When a ship is built, it's usually given a hull number. Hull numbers are unique, even if the ship changes names, right? Owners, whatever. So at least in most navies will assign a ship hull number. So basically, the hull number can be the key, and the ship name and the ship data, like what kind of ship it is, can be all the value stuff. So the values. So remember, keys are unique. Values can be basically anything, from a string to a structure of data, right? If it's like a bunch of data, a value can basically be anything. but a key has to be something that is, quote-unquote, well, let's not say that yet. So that's basically the idea of a map. It's something where you have a unique key that can access any particular thing. And so, I don't know if you remember, or maybe you do or don't, in Python, for instance, we have a map object. It's not called a map in Python. It's actually called a dictionary, right? So dictionaries are maps. Dictionaries, they implement, I should say this, dictionaries implement the map ADT. Even better, dictionaries are hash tables. Now is the time to ask, okay, so what is a hash table? Right? And so a hash table is a map, right? So the reason why we make a distinction is because there are other ways to implement the map abstract data type. A map abstract data type is just something where you have keys, you have values, and they're associated, right? A hash table is a specific data structure. So now let's get into hash tables, right? Okay, so a specific implementation of map ADT. So now what are hash tables? Well, that's the whole point of the project. That's the question you're asking. So a hash table basically is a souped up array. That's all it is, okay? It's an array. Now you might be asking, well, hey, hang on, right? How on earth am I going to store phone numbers in an array? Do I need billions and billions of entries? And the answer is you generally don't, and let me explain why you don't. So instead of using the indices as is, we do something to the key values, right? We don't actually just go array at key. We don't do this. This is an array, right? But we want to make it into a hash table. So to make it into a hash table, we invent a hashing function. Okay? So what is a hashing function? A hashing function which takes our key. Now our keys can be anything. So our keys can be strings, they can be ints, they can be technically even doubles, they can be bools, though that's kind of pointless. And you'll see why it's pointless, because there's only two things. But so the thing is that the common things are either some kind of string or some kind of integer. It's much more rare to make. It's actually a bad idea to make your key into doubles. The reason why is round-off error. So it could be dangerous to make a double into a key, because then you might actually never be able to find the stupid thing again. So, you know, if you do a calculation two different ways and you can't find your key anymore because the computer's done a round-off error in one direction. But strings and ints are pretty good for hashing. So let me give you an example of a hashing function. Here's the simplest hashing function ever for ints. Okay? And so Python actually kind of uses this to some extent, but so now our array has some length, right? Say its length L. All right? Here's the hash function. H of key, which, and remember this is an integer, right, is going to be equal to the key mod L. Or you can write it as key mod L. Right? That's it. That's the simplest hashing function. Right? So for instance, and then this is exactly how you insert. So let me show you an example. Well, okay, I really want this, that. Let me show you an example with, say, 5 elements, right, in a little mini hash table like this. And so let's put some, well, no, okay, so let me just label the indices. I was about to say let me put some stuff in here. I do not want to do that because we have not yet inserted. Okay, I want to do this. Okay. So, what if I say I want to store okay, let's actually store strings. So I want to store happy, or let's just do letters like H in for key 17. So basically, whenever I call up 17 as a key, I want H to come back. Okay? So now here's the question. How do I store this in our little hash table? So the answer is what we do, we take the key, right? 17. Well, 17 mod 5 is equal to 2. Okay? So we store it in, and I should say H. We store H in slot 2. So now let's put H in slot 2. There we are. Okay, now let's do it again. Let's store key equals 33, or yeah, let's make it 35. Value equals R, right? And so in order to do this, what we're going to do is we're going to say 35 mod 5 is equal to 0, right? And so in slot 0, we're going to store an R. And then you're going to ask a question in a second, or you're going to be thinking about a question. That question is going to be a reasonable one. But I'm going to tell you, that's the whole point of this lecture. So let me, there we go. Okay, sorry, I just wanted to save it so that I didn't end up crashing. So now let's store say 14, 14 maps to, what should 14 map to? 14 is going to map to Z, right? So 14 mod 5 is 4, so now we're going to store Z in here. Okay, all of that's been good so far, right? To which you say, okay, well, hash tables are pretty freaking easy, right? And now, let's say that, okay, so now I want to recall element 35, right? So what I do is I say, okay, I'm going to hash 35, which means 35 mod 5 is 0. So then what I do is I look in slot 0 and I get R. Good. So we can go backwards. All right. So here's the problem with hash tables, and this is basically where the project starts, is, okay, I'm going to zoom out. Okay, there we go. So what are we doing here, right? Let's say now that I want to insert element, say, I don't know. Key is going to be 20, and it's going to map to P, the letter P, okay? All right, that's fine. We can do that. But then what you do is you say, okay, 20 mod 5 is equal to 0, so put P in slot 0, right? And then what do we see? Here's the problem with hash tables. Uh-oh. No, we can't. There's already something in there. Right? So that's the problem. Right? So basically the idea here is, and let me just secretly store the values or the keys up here. Let's store the 17 and 14. Okay. So usually you'll store the key along with the value as well. So this is basically what you're going to end up with, is some kind of struct with a 35 and an R in it. You'll end up with a struct with a 17 and an H in it. And you'll end up with a struct with this. But the point is that now that we go into here, we see that slot 0 is already occupied by something, right? And so basically, this is called a hash collision. Okay? So hash collisions are generally bad. Well, yeah, they are. Because what it means is that we're starting to overlap where we can put elements of the same, not the same key, but the same hashed value, right, of their key, right? And so that's the problem. And now you notice that it really doesn't matter how complex our formula is, right? If our formula was like, if instead of being just h of x is equal to, or h of k for the key is equal to k mod 5, imagine that our formula was h of k is equal to k squared plus k minus 2 mod 5, right? We still have to mod 5 because that's the number of elements in there, but imagine we did something more complicated. Notice that it still doesn't matter because the thing is that we're still going to get overlaps eventually. If you insert 5 elements and then you try to insert a 6th element, then you're still going to get a hash collision, right? So the complexity of the hash function, all the complexity the hash function does is, so yeah, I'll explain that. The complexity of the hash function generally is meant to ensure a uniform distribution of key value pairs. And what do I mean by that? What I mean by that is that you could have the worst hash function in the world, h of k equals 0. So we have this array. So here's the worst hash function. And so why is it the worst? It's the worst hash function because it's just going to keep trying to store everything in slot 0. All keys hash to the same value, right? So that's a pretty bad hash function in the sense that it doesn't ensure, I mean, it doesn't ensure any distribution, definitely not a uniform distribution. No. So hash collisions don't cause segfaults, right? Because there's no pointer problem yet, right? We're not going to actually insert on a hash collision. So what are we going to do, right? So let's look at our little thing, and let's actually, so let's think of some solutions, right? So I'm going to start with the solution that the project doesn't use, because I think it's actually one of the cooler little solutions. So, so here's the non-project solution, chaining, okay? So basically, instead of each one of these things being a single element, what it is that each one of these is the head of a linked list. So what happens is that when we try to insert 20 at slot 0, what's actually going to happen is that we do something like this, where we do something like that. And then what we're going to do is put 20 into this slot. So this is one way of resolving the hash collisions, okay? And so for instance, if we were going to insert, let's say we inserted 15 maps to A, right? 15 is also 0 mod whatever, mod 5. And so here what we're going to do is we're going to do the exact same thing we did, and we're just going to keep appending to our linked list, right? So we're going to keep adding to our linked list, right? And so this is definitely one way to solve the problem, right? And then let's say that we insert 104, and that maps to, I don't know, T, right? And so if we insert that, then we have to do 2 linked list chains, right? So this is basically how we do it. Let's delete that 0. Here we are. Here we are. So this is one way to deal with hash collisions, all right? And so hash collisions can be dealt with this way. And then, of course, if you want to delete something out of the hash table, all you have to do is go through the linked list and delete that entry, okay? So inserting, the only problem with this is so let me explain what the benefit of a hash table is. Okay, so we assume that hash function h of x takes O of 1 to run. Okay? It's not dependent on the size of the hash table. That's what we assume. Now, you might be able to say that it does depend and blah, 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 blah. Assume it doesn't depend on the size of the hash table, right? If that's the case, then what is the cost of an insert operation, right? The cost of an insert operation is basically the time of an insert operation equals cost, right? Is equal to the time that it takes to do an insert in an array plus the time of a hash function, right? And so what do you know? You know that the time that it takes to insert into an array is O of 1. The time that it takes to do a hash function is O of 1, because we assume that. So it takes O of 1 to insert. Wow, cool. And then what's the time for find, right? Well, that's also time of hash function plus time of access an array index, which is also equal to O of 1 plus O of 1. Right? So, still way cool. So that's why Python uses dictionaries. That's why hash tables are really useful. And the reason why they're useful is because their insert and their find are both O of 1. Now you remember for like a binary search tree, right? Or for like a balance like an AVL tree, insert and find are both O of log n, right? Delete is, so this is time of insert or time of find, right? Also equal to time of delete, right? So basically insert, find, and delete all run in O of log n time, which is not constant time. Here, for a hash table, it takes constant time to access things, right? And you're like, wait, but so why didn't we just do hash tables from the start, right? Why not just always do hash tables? And the answer is actually, most of the time you actually do just do a hash table, but there's a cost, right? The cost is that a hash table is an array. And what is the problem with an array? So the nice thing about a binary search tree is that you can keep inserting elements. You never actually have to rebuild it. So there's two costs. One cost is that generally what you have to do, a low load factor. And so what that means, and let me explain what the load factor is. The load factor is usually denoted lambda of our table, is equal to the number of filled divided by the number total in the array. So this is the total size of array. This is the number filled in the array. And so why do we have to maintain a low load factor? Generally, we want the load factor, and in our project, we want the load factor to be less than 0.5. And the reason why is because if you have a low load factor, there's less of a probability of a hash collision, right? If you have 99 out of 100 array slots filled, and I give you an element, and I say, what's the probability of a hash collision with a uniformly distributed key and uniformly distributed hash function, you would say, well, the probability of a hash collision is like 99% now, right? And then you either have to do chaining or what I'm about to explain once I get through the chaining part. So here, right, so this is one way to combat hash collisions, right? But this comes at a cost, because if you end up, let's say that you pretend that these are other elements that also have this. I mean, I'll just delete that so that there we go. So here you see that we're running into a problem with this version of hash collisions, right? If we just do chaining, right, with linked list, then what you're going to say is that if we end up with a lot of collisions at the same element, then this starts to look like a linked list, not a hash table. And you know what the problem with that is. Like, the problem is linked lists run in O of n time for insert, find, whatever. You can run you can actually run the linked list in O of 1 time if you're willing to like insert at the head and then delete from the head or whatever. But find is still, so insert can maybe be better, but so the thing is that linked lists run in O of n time, not O of 1 time. So this is the other cost. This is the danger, I should say, of a hash table, right? If it starts to look like a linked list, the problem is that the linked lists run in O of n time, not O of 1 time, and then we lose the hash table functionality, basically. Basically the hash table ends up just being like a bunch of head pointers to linked lists, all of which run in some O of n time. So it's all kind of bad, right? So, is there a better way to do chaining, or is there a better way to do collision resolution than chaining? And the answer is, well, so there's no reason that you had to use a linked list here. You could have used, for instance, what if you used an AVL tree here instead of a linked list? And the answer is, okay, well then you just improved the runtime of a hash table to O of log n rather than O of n. So that's good, but it's still not constant time, right? And so let's talk about another example. And so this is one of the 2 project examples. So let's go through and talk about, so the project solves this problem in 2 ways. And I shouldn't, I'm saying the project, but really what I mean to say is that these are standard solutions that we always learn in 341, but the project uses them, right? So the project doesn't invent these two. These 2 processes are not invented by the project, but the project does use them. So what does the project want you to do, right? The project wants you to use. So let's start again at this point, and let's try to insert 20p, okay? So we want to insert 20p. Now here's how I'm going to do it this time. So I'm going to talk about a method called linear probing. I almost forgot the word probing. Linear probing. So what does this method do? So what this method does is no linked lists, no auxiliary data structures. Everything is stored inside the array itself, okay? So the idea here is that everything is stored inside the array. So what are we going to do? Well, you're saying, you tell me 20p gets stored in slot 0, but there's already something in slot 0. So linear probing, it's as dumb as it sounds. Go to the next slot. There we are. That's it. That's what linear probing is. Now you notice that there's an issue that linear probing causes because let's insert the other one. Let's say we insert, and now of course we're about to get to a filled hash table, but maybe we'll make a bigger hash table and then do it again. So what if we were going to insert 15a? So 15a tries to insert here. It can't. So it goes to the next one. It can't. It goes to the next one. This one doesn't have the right key value. It still can't insert there, so it goes past it and inserts here, right? So basically what you do for linear probing is you scan through your array in a cycle. So what I mean by that in a cycle is that if you reach the end of the array, you go back to the beginning and make sure that there's no empty spaces at the start. So go from position I to position end, then back to 0, then up to I minus 1, right? So check every position in order. And so what you're going to do here is you're going to scan through in a cycle, and the first empty space you'll insert there, right? Now, of course, so the issue that this creates, insert and find are no longer O of 1 in worst case, right? And here's the reason why, because insert and find are now O of n in worst case. because what you know is that you have to scan through the entire list. The entire list is of size n, and if everything is filled, then that's what you have to do in order to prove to yourself that you can, I guess technically if it's like n minus 1, then you have to scan through the whole list to find the empty space. But this is the way the project does it, so that's the idea. And so now the question is, how do you find? And the answer is you do find the same way you do insert, right? And basically what I mean by that is that you insert the same way you find, so or find the same way you insert. So if I wanted to find element, say, 15, then what I do is I say I'm going to hash the key, right, which is 15. I don't know what the value is because that's what I'm looking for. So I know the key is, I want to get the key, I want to unlock the door with 15, right? So I say 35, are you the right thing? No. And then I have to linear probe again, right? I have to say, okay, 20, are you the right thing? No. 17, are you the right thing? No. 15, are you the right thing? Yes. Okay. So now let's do some more examples of linear probing. I need to make this a bit longer of an array, so let me delete all this crap. And let us make the array size, let's make it size 11 to start hinting at primes. 5, 6, 7, 8, 9, and 10. And don't worry, I will not leave it in that state. There we go. So now let's start to insert things. Now we're going to insert things with the function h of x is equal to x mod 11. Okay? So simple hash. Actually, let's do it with 3x mod 11. Okay, so we'll have to think a little bit. So let's insert an element. Let's insert 15 and, a. So 15 mod, okay, we got to do 45 mod 11. 45 mod 11 is 1. Right, because 45 is 44 plus 1, so that's where it goes. All right, now let's insert, say, 24b, right? And so let's insert b at 24, so 24 times 3 is 72. 72 mod 11, so 66 is the one, so then I think it's 6, right? Let me just double check some of this stuff. And then mod 11, yep, 6. I almost didn't trust myself for a second. I just don't want to make any mistakes. So let's insert at, 31, let's insert t. So 31 times 3 is 93. So 93 minus 99 is minus 6. So plus 11 is 5. So that's going to go at element 5. And let me just move this one down here. I'll move this one up here. Okay, so let's try another one. Let's see, what's something else that inserts at element 5? So let's solve 5 equals 3x plus, mod 11, so the answer is 5 plus 11t is equal to 3x. So that means that if t is equal to 2, that's 27. Okay, let's do 27. So let's say x equals, or x equals 9, t equals 2. So you generally don't have to do this kind of algebra. I'm just doing it because I want to solve for something that also hashes in there. So am I right to say that if we have the value 9 and we hash it into, let's say r, or I'm sorry, 9 is the key, r is the value. So what's going to happen, right? So 9 times 3 is 27. 27 mod 11 is 5. So, okay. So now we try to insert in slot 5, right? All right. So inserting into slot 5, we can't do it. So here what we're going to do is we're going to insert into slot 6, can't do it. Insert into slot 7, we can't do it. Right, so that's the point. Okay? All right. So basically, okay, let's insert a few more elements. Let's insert, I don't know, 51z. So 51 times 3 is 103. 103 mod 11 is, can I do this in my head? So, 7. No, 4. Okay, yeah. See, that's why you should never do it in your head. So, okay, so 51 goes into slot 4. And so now what? So let's keep going. Let's insert another one. Let's say 7 and p. So 7 times 3 is 21. 21 mod 11 is -1, so it's, I guess, what, 10? So this should go into... Let me just double check that. So 21 mod... Of course, never mind. It goes into slot 10. I don't need to check that. All right, so you see how this is working, right? Now, what if we got something else that went into slot 1? So let's pick something else that goes into slot 1. What else goes into slot 1? Let's solve for it. So 1 is going to be equal to 3x mod 11. 1 is equal to 3x plus 11t. So 1 minus 11t. Really, we can just put 1 plus 11t equals 3x. We can put this as a minus. And then what we do is we just kind of look for it. So what we're going to do is we're going to say, when do we get to something? So, t equals 1, x equals 4. So let's do it. X equals 4. That was simple. So now let's insert 4, and then let's say y. Okay, so 4 times 3 is 12. 12 mod 11 is 1. So we're trying to put it in here, and we know we're going to do we're going to see a hash collision, so we go here. So basically, here's a question, right? What if we are looking for something with a key value that hashes to 6, but isn't 24? So let's solve for that too. Let's say 6 is equal to 3x mod 11. 6 is equal to that. 6 is equal to that. So I guess maybe if I set t equal to 3, we'll get 39. 39 divided by 3 is 13. Okay. So if let's say we search for 13, right? Right, and so what we do is we plug it in the hash function, 3x mod 11, and what we get is 3 times 13 mod 11, which is equal to 39 mod 11, which is equal to hopefully 6 in this case, because I've solved it for that. And so we know that the hashed key, or the hashed so the hashed key is 6. And so what we're going to do is we are going to look through, and we're going to say, okay, is this equal to 13? No. Right? So we didn't find it. Now here's the thing, right? What we're going to do in order to find this key, to see if we can find 13 here, is we are going to search the next spot. And now you might remember that the next spot, this 9R, actually was a collision with this, not with this. So it was a collision here. But the thing is that the data structure doesn't know that, right? So all we know is that we're testing, is 9 equal to 13? And the answer is no. So we test if 24 is equal to 13, no. And then we test if 9 is equal to 13. Okay? No. And so then we test if blank equals 13, stop, right? And so that's how we know that 13 is not in the structure. Okay? So that is a hash function with linear probing, right? Linear probing just means you keep going on to the next one, either for insert or for find, until you have either inserted the element into a blank space. Like for instance here, if this were insert, and we were trying to insert, say, 13 Q, then the answer is actually that 13 and Q would go into here, right? So if we were going to insert it, then it would go into this slot. But since it's not there yet, then there we are. Okay, so that's how this stuff works. That's how linear probing works. So, okay, let's go over the other method, right? And let's do it with a much simpler hash function. The hash function we're about to use is h of x equals x mod 10. All right? And let's delete all the entries here because they're all wrong now. Here, 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 here. Okay, so that's linear probing. Linear probing just says go on to the next element until you find the thing or until you're done. What does quadratic probing say? And you might say that, like, quadratic probing, in a way, it's better at getting a wider distribution of elements. So the advantage of it, whoops, distributes elements more widely, right? And disadvantage requires knowledge of quadratic reciprocity. Just kidding. But also kind of not. So, okay, so I've told you that we're going to use a different method of probing, and so here's what basically, quadratic probing is an attempt to solve this problem, right? So here's the problem that quadratic probing is attempting to solve. Look at what linear probing does, right? You know, you might say linear probing kind of bunches elements up when we have duplicated hashed keys, right? Not the exact same key, right? If you have the same key, then that's the same exact thing and you're in the same spot. But if you have a duplicated hashed key, like for instance, you want to stick something in slot 4, but something else is in slot 4, or you want to stick something in slot 5, but something else is already in slot 5, so then you have to start going and you go next, 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 next. But you see the problem here, it kind of bunches this stuff up, right? It bunches all this stuff up in a way that causes even more linear probing to go on, right? So if this starts to do linear probing, then this one is going to start to do linear probing too, because it's going to start having elements after it. Basically, all the elements around it are going to start having to do linear probing as soon as you start doing too much linear probing for insertion, right? And so that's the danger here of linear probing, is that it's going to trigger clumps of data. And so remember what I said earlier, is that our goal in a hash table is always to try to maintain equal distribution of elements when we can, right? And the reason we do that is so that we don't have hash collisions, right? And here we're kind of guaranteeing ourselves a bunch of hash collisions. So linear probing has its flaws, right? So people came up with quadratic probing, and you might ask, well, what the heck is that? Here's what it is. So instead, so basically, in order to do linear probing, right? Linear probing takes the hashed value, right, h of x, and we add I, and we mod it by the size of the array, right? So that's linear probing. Here's quadratic probing. And I'm sure that you probably can guess by now I've been hinting at it for a while. There we go. There we are. So that's what quadratic probing does, where, and I should specify, where I is the number of times we have to search, or I should say probe. Right, so if we probe 0 times, if we just go straight into the slot, then the hashed key is h of x. But then what do you see here? So let's insert a bunch of stuff into this hash table and just see what happens. So let's insert something, say 5a, right, into this hash table and see what happens. So 5a is just going to insert with I equals 0, right? I equals 0, so it's going to go straight into here, 5a. There we go. And now I'm not even going to worry about, well, let's insert some other elements. Let's insert, say, 3p, right? And so 3p is going to go into the slot 3. There we are. Let's insert something in slot. Now let's not insert anything in slot 9 yet. Okay, let's insert something into slot 5 again. So let's insert 15r, right? And so the point is that 15r is going to give us the hashed key is equal to 5, but there's something already in there. So it's going to start looking like linear probing to start. So we're going to go h of 15 plus 1, right? Because 1 squared is equal to 1, so this is just h of 15 plus 1 equals 6. So we're going to try to stick 15r into slot 6. But then what are we going to do? So let's say that we have to do it again. Let's insert 25t, right? So 25t is going to hash the same value. So the hashed value of 25 is equal to 25 mod 5. 25 mod 10, which is equal to 5. But then you say, okay, 5 plus 1 is equal to 6. No good, right? So 5 plus 0 is equal to 5. No good, right? 5a already there. 15r already there. So now, remember that we're not doing linear probing. This is not 5 plus 1, 5 plus 2, 5 plus 3. We're going to do 5 plus 4, right? Because that's 5 plus 2 squared is 5 plus 4 is equal to 9, technically mod 10. Okay, insert there. So what we're going to do is we're going to insert 25t in slot 9. Right, and so that's how quadratic probing works. What it does is it says, first you insert at the slot where the hash key is. And then you insert at the next one, right? Because that's plus 1 squared. But then you say 5 plus 2 squared. Well, 5 plus 2 squared is 5 plus 4. 5 plus 4 is equal to 9, right? Let's do it one more time. Let's insert 35z, right? And so if we insert 35z, then the hashed key of 35 is equal to 5, right? 5 plus 0 is 5, no good. 5 plus 1, right, times 1 is equal to 6, no good. 5 plus 2 times 2 is equal to 9, no good because we just inserted something there. So 5 plus 3 times 3 is equal to 5 plus 9, which is equal to 14, right? So at that point, we have to mod it again by 10, so go into slot 4. So what that means is that we are going to insert 35z into slot 4, right? Okay. All right. So we see that this is kind of, I mean, it's not really distributing it that evenly because it's kind of doing this here and this here. But you see that it's kind of trying to space them out, right? Because it tried to space this out 9 steps. The problem is that it's of size 10, so it loops back. So that's an issue. Yeah. So what else is there to talk about here? So here's the issue. Let's say that we tried to insert something with a hash of 3 again. So if we insert, say, 13 Q, then the issue is that what's going to happen? So 13Q is going to give us the hash of 13, which is 3. 3 plus 0 is no good, right? 3 plus 1 is no good, because that's equal to 4. 3 plus 4, right, 2 times 2, is equal to 7. Okay. So now this is a little bit confusing, right? Because if you think about it, which ones are which ones? And the answer is this one, and this one, and this one are all associated with the key 5, and this one and this one are associated with the key 3, right? So this is how quadratic probing works. Now, here is the issue. So here's how quadratic programming works. Yes, good. But here is the issue with quadratic probing. So the issue with quadratic probing is this. Let us look at the quadratic residues, meaning the things when you mod. So if you take, say, 0 is equal to 0, mod 10. 1 is equal to 1 mod 10. None of this is surprising. 4 is equal to 4 mod 10. 9 is equal to 9 mod 10. Okay. What is 16, right? Right, what is 16? 16 is, well, not a problem yet. It's 6 mod 10. So notice at this point, they're all different. Okay? They're all different here. All right. Now let's do 5, right? So 25 maps to 5 mod 10. Good. And at this point, they're all different. But wait, what happens next? What happens next is that 6 squared is 36, right? 36 is the same thing as 6 mod 10, right? But we've already seen a 6 mod 10. So what can happen is this. So basically, 36 is 6 mod 10, but we've already seen this before. Okay? We've already seen that one before. And it's the same thing if we keep going. So 7 squared gives us 49, but you'll say, wait a second, I've seen 9 mod 10 before. This one too. What about the next one? So that is 6 and 7, so what about 8? So 64, right? 64 gives you 4 mod 10. Yep, seen this one. And then what about 81, right? That's 8 squared, so let's do 9 squared is 81. Is 1 mod 10? Also, yes. Huh. Right, and the other thing you might notice is that it actually goes in reverse order, so you see here it goes 1, 4, 9, 6, 5, and then you see 6, 9, 4, 1, right? 6, 9, 4, 1. So you see that they go in reverse order, and then of course if you plug in 10, you'll get 100, but this is not terribly surprising. Mod 10, also, yes. So, here is the problem with quadratic probing, okay? The problem with quadratic probing is that when we square a number and mod it, there is not always a solution to each index. And what I mean by that is that there's not always a way, an I, so that I squared is equal to some index, right? Whatever index I pick. So for instance, if I said, let's try to solve for I squared is equal to 3 mod 10, the answer is, okay, so you scan through all of these, and as it turns out, it just loops back over and over and over. If you go to 11 up to 20, if you keep if you keep going up, it's just going to keep looping through these things called residues. And so the problem with quadratic probing is that here there's no solution, right? So the advantage of quadratic probing is that it it more evenly distributes the elements, in the hash table. And disadvantage, and so this is what I was saying when I was joking about it requires knowledge of quadratic reciprocity. So the joke is, I'm just kind of joking that you don't really have to know that much about quadratic reciprocity. All you have to know about it is that there's not always, it won't fill up a table completely in all cases, right? And the reason why it won't fill up a table in all cases is because there's some squares, or there's some numbers where there's no way to get there by a square. So, if you square 1, you get 1, 4, 9, 16, 25, which looks like 1, 4, 9, 6, 5, and then you get 6, 9, 4, 1. So there's no way to get to 3, right? If your key hashes you to 0, for instance, let's say that your key hashes you to 0, and 3 is empty, right? 3 is empty, maybe 2 is empty, are empty. There's actually no way to fill in those array parts, or those array indices from h of key equals 0, right? Now, this all gets shifted, so there are ways to fill in, if something hashes to 2, you can fill it in, but with the probing, you can't fill in something that is offsetted by 2 or 3, generally. At least if, again, if you have a list size of 10. Okay, so that's the point. That is basically the project. So the project is that you have to implement both linear and quadratic probing. And so what you have to do for the project is you have to switch back and forth. So this is a part of the data structure. So let's say, basically what you have to do is you have to, when your load factor, which remember the load factor lambda is equal to the number of filled slots over the number of total slots, right? When this is bigger than 0.5, what you have to do is you have to make a bigger array, right? And so what we're doing there is increasing the denominator, right? So we're increasing the denominator, so that'll lower our lambda, right? Overall, it's going to take our lambda down to a lower level, which will make it good. But then you have to basically recopy everything into the new array. But here's the catch. One, you can't just do that, right? And so the question is why. The answer to that is because once you have a new size, right, you can't just copy everything into the front part of the array. You have to rehash everything, right? Because now the total size in the array is different, right? So the mod that's at the end is different. So everything has to get rehashed and remodded, okay? You have to rehash everything, remod all the keys. You have to do that. It sucks, but you have to do it. And then the other problem is, 1b, is, let's see, you have to rehash everything, that's 1a, and 1b, you have to alternate the type of probing. So for instance, if you used linear probing before, you have to use quadratic probing now. And then switch back if you have to do this. A second time, and then the third time you'll switch back from quadratic to linear, then the fourth time you'll switch back from linear to quadratic, the fifth time you'll switch from quadratic to linear, etc. And I might explain this next time because I'm way over time, but I'll explain this next time. So the second thing that you have to do is, how much bigger do you have to make the new array? And the answer is you have to make it at least 4 times as big. Right, so at least 4 times as big as the previous array. But, so basically you need to scan above 4x until you find a prime, and then that's the new size. Okay? So basically, if your current array, let me just do an example or two before I let you go. But so if your current array is size 5, then 4 times 5 is equal to 20, which is not prime. It almost can't be prime by definition, right? Because we're multiplying it by 4, and so that makes it a composite number, so it can't be prime. So we have to search up. So we say 21, 22. So 21 is 3 times 7. 22 is 11 times 2. 23 is prime. So there we go. Right? So now let's say our current array size is 23, right? So 24 times 23 is equal to what? I guess that's 80 plus 12, so what, 92? Right? 92, not prime. Can't be prime, right? Because it's 4 times something. So what we're going to do now is we're going to look after 92. We say, how about 93? Well, that's 3 times something. 94 is even. 95 is divisible by 5. 96 is divisible by 3. 97. Is 97 prime? I think it is. Right? So that's our next one. And then, for instance, if our current array size is 97, then 4 times 97 is equal to what? That's 400 minus 12, so 388. And so basically at that point, again, not prime. And so what you have to do is you have to find 389 seems prime to me. I don't know if it is or not. Actually, it is. Lucky us. That's kind of amazing. So 389 is prime. It felt prime. And it is. So because it felt prime, and in my internal prime computer that my feelings. So that's the point. I won't go any further, but that's basically how you'd have to do this. So if your starting array size was 5, once you get like 3 elements in there, right? Once it's at least half full. So basically this triggers at at lambda, well really I should say at the number of elements is, or let's just say k is equal to 3, right? After 3 insertions, this triggers at, say, k is equal to 12, I guess. So at 11 is slightly less than half, so it's okay. 12 is slightly bigger than half, so it triggers. This will trigger at, what does it trigger at? K equals, and let me just say k is equal to the number of insertions. It'll trigger at k equals what? 97 divided by 2, so what is that? 49, I think, right? Because you have to round up. It's like 48.5, but you got to round up, so it'll be 49. Because it has to be bigger. It can't just be equal or slightly less than half. It has to be strictly bigger than half. So 48 won't trigger it, but 49 will trigger it, and then you have to build the whole thing up again. So basically next time what I'm going to do is I'm going to go over reconstruction of hash tables from other hash tables, and maybe I'll implement a hash table with chaining resolution, and maybe I'll even do an example with like cubic probing, right? Where instead of doing I squared, you do I cubed. Because that's not the project. So then I can actually release that on GitHub. Honestly, it's all very similar, but that's the point. So I think that's basically it for today. I think I've kind of described what a hash table is. A hash table is a big array, right? You stick things in based on a hash function. You try to stick them in equally distributed. Sometimes you can't. When you accidentally stick something into the same slot, then you have to do one of two things. Either you got a chain or you got a probe. If you chain, you'll end up with a linked list or an AVL tree or some other kind of data structure. If you probe, you end up with something like this. And then there's the two kinds of probing that they usually teach. There's linear probing, where you just keep going to the next element. And then there's quadratic probing, where you add an offset, which is the square of the index that you have to go to. So if you have to probe twice, then you'll go to 3 plus 4, or the index hash key plus 4. And if you have to probe again, then you'll go to the hash key plus 9, and then hash key plus 16, hash key plus 25, etc. And of course, you still have to mod by the length to stay inside of the array. Okay, so we'll talk more about reconstruction next time. I mean, basically, there's nothing terribly complicated about reconstruction of the hash tables. It's just you literally have to scan through your old hash table, allocate the new hash table with the new size, rehash all the stuff, and reinsert. So it's a total reconstruction. It's a very inefficient process, right? It's generally an O of n process, since it requires total reconstruction and rehashing and reinsertion of all elements. Right? So there's no silly trick here. There's no trick. You just have to do it. All right. So that's really it for today. We will get back to, we'll do some more coding with hash tables next time. I'm sad I didn't get to cover binomial heap coding as well as I'd like to have, and Fibonacci heaps just totally got skipped. I might go back or I might not, but we'll do more on heap or hash tables next time. Okay, that's it for today. I'll post these now, and that's it. Like 10 minutes over as always.